first period, so second chance, you guys. Are there any questions over the homework? Yes, Carly.
For number 29, how did you get 8?
So I kind of did the work on A. The disk. So H is right here. It's going to be the length of the rectangle. And because it's going horizontally, we know it's going to be right minus left. And the right is the curve. The left is the y-axis. So it's going to be the curve minus 0. But it's a dy problem, so we have to take the curve and solve for y. And I actually had taken the equation and up here solved, solve for x to put it in terms of y. Anyway, I had already solved for y up here, but because of the way the symmetry of the equation is, the work for solving for x is identical, just the x's and y's switch places. So I used this then as my equation of the curve. So I just didn't show that. Any other questions about the homework? Pi Day. It's a good day. I'm so bummed, though. I forgot to wear my Pi Day shirt. Carly, yes.
Can you also go over 45A?
Yes. If I can find it. Whoop, was that it? Nope, that's 43. 45A. Use differentiation to verify. So, what they're talking about there, if the antiderivative of this is that, the derivative of that should be this. So I'm taking the derivative of that. And derivative of sine is just cosine. I have to do product rule right here. So it looks like I chose to put the minus sign outside and then do first times derivative of the second plus second times derivative of the first is just 1. And derivative of c is 0. And then playing around with this, we can see we'll get x sin x. Any other questions? Because we're going to have some fun today. It's Pi Day. You gotta have fun, right? I think you'll like this. It's arc length. What's not to like about arc length, right? All right, then. Well, let me go ahead and have your homework then. And we do have a reality check, though. I will pause the recording. There's number 1. Any questions about number 1? Yes, so. Yeah.
On the test, if we draw out the graph, will we get points taken off, like if we draw the graph incorrectly, but we still get the right?
See, that's actually why it's important to draw the graph. So if you'll lose something for having the wrong graph, but if you do all of the other work correctly based on the incorrect graph, you'll lose just like 1 point. It'll just be a minor part. So, yeah. Good question. Any other questions? All right, let's do number 2. Number 2, gotta watch out for this one. Be careful about the radius. The radius only goes halfway. That'll be one of the most common mistakes students make with the semicircle cross sections. So when you draw the picture, this represents the diameter of the cross section. So top minus bottom is not the radius, it's the diameter. You have to divide by 2 to get the radius. A lot of people forget that. Any questions on this one? Anybody want more time looking at this one before we go to number 3? Number 3. Be careful with P. Remember, you always got to measure right minus left. So it is 1 minus x, not x minus 1. Any questions? How about we do the last thing for this unit then? Arc length. Yeah. Oh. Arc length. Let's move this to its own page. Oh man, it's the same thing. Ugh, that was painful. Okay. Arc length. Actually, the title of this section is arc length and surface area, but we are not going to do surface area. Only arc length. Sorry. We'll do surface area next year in BC. Yay! All right, arc length. So we're going to do this. So we're going to derive the formula, and then we've got 3 examples we're going to do together. And then that's it. So to derive the formula, we're going to do something similar that we've done in the past. When we were trying to find area under the curve, we tried cutting up the area into rectangles. And then eventually we could fit an infinite number of rectangles to make the actual area. When we were doing volume, we cut up the volume into discs, washers, or certain cross sections. And again, the idea was once we could fit an infinite number of them in there, we had the actual volume. Well, this time we're doing arc length. So to do arc length, we're going to cut it up into line segments. And then try to fit an infinite number of line segments in there, and eventually we'll have the actual arc length. So a picture that we're going to start with will look something like this. We'll put an X and a Y axis on there. And I'll just put, how about this curve? We're going to find that arc, the length of that. It was a piece of string and we pulled it straight. How long would it be? So I'm going to cut this up. For this example, I'm going to cut it up, looks like into 4 line segments. So if I could add up all these line segments, it would give me an approximation of the arc length. More line segments, the better the approximation. I'm going to label these points. First point will be x1, y1. Well, actually, sorry, doesn't really matter, but I'm going to make it x0, y0. Then x1, y1. Then x2, y2, and so on. And because I had 4 line segments, I'm going to end with x4 or y4. And let's name these line segments. L1, L2, L3, L4. Does anybody know in math what letter we typically use to represent arc length? What variable? We use the letter S because there's not a single S in the words arc length. Yes, arc length, right? We're going to let S represent the arc length. I'm guessing, I don't know for sure, I'm guessing it's from another language. There's probably another language the words arc length begin with S. But that just has kind of become standard. Or it's arc length, yeah. So, arc length, S, is approximately the sum of the length of each one of these line segments. only we had a way to find the length of each one of these line segments. Like, you know, a way to find the distance between the two endpoints of each one of these line segments. If only we had a formula to find distance. Ah! So yeah, we're going to use the distance formula. So the first line segment would be x1 minus x0 squared plus y1 minus y0 squared. And then remember, all of that is in a big old square root. And then L2 would be x2 minus x1 squared plus y2 minus y1 squared. All under a big old square root. And we can keep going, but I'm not gonna. Let's generalize. But any questions so far? So in general, I can say that the ith line segment, L sub I, is x sub I minus x sub I minus 1 squared plus y sub I minus y sub I minus 1 squared, all under a square root. Ugh. But that's kind of wordy, even though there's no words. I'm going to take a little liberty here. I mean, x1 minus, or xi minus x sub I minus 1, that's just the difference of x values. Let's just call it delta x. And the same thing with the y's. So why don't we say this, that in general, the length of one of these line segments is delta x squared plus delta y squared under a big old square root. Ah, that's much better. I like that. All right, any questions so far? Now remember, that's just one line segment. So for the arc length, we'd have to add up all the line segments. And we could turn that into a sigma. Yeah. So we can say the arc length is approximately the sum of the square root of delta x squared plus delta y squared as I goes from 1 to n. That will give us n line segments. So it's just an approximation, not an infinite yet. Now eventually I'm going to do the limit as n approaches infinity and get the actual arc length. But my whole goal is I want to be able to take this Riemann sum and use the definition of definite integrals to rewrite it as an integral. But in order to do that, I need a delta x at the end that will turn into my dx. Right now I don't have that, so I'm going to play around with this a little bit first. Won't be very much though. I'm going to factor out a delta x squared from inside the radical. So it's going to look like this. Arc length is approximately the summation as I goes from 1 to n. And then inside the square root, I'm going to have 1 plus delta y squared over delta x squared. And then that's times delta x squared. And I still have that big old square root. And you can check that this works. If you distribute that delta x squared back in, delta x squared times 1, delta x squared times a fraction. The delta x squareds cancel out, you have delta y squared. And then in the next line, I'm going to do two things. First of all, this delta y squared over delta x squared, the top and the bottom are both squared. I'm just going to make the whole fraction squared. And then when I take the square root of something squared, they'll cancel out, and I'll just have delta x left. So it's going to look like this. I still have a summation as I goes from 1 to n. And then inside the radical, I'm going to have 1 plus delta y over delta x all squared. So that's still in a square root. But then outside the square root, I'm going to do the square root of delta x squared, which is just delta x, no longer in a square root. And now I got the delta x on the outside that I was looking for. That's going to turn into my dx in the integral. So, now I can say the arc length, not approximately anymore. The arc length is equal to the limit as n approaches infinity. So that's going to give me my infinite number of line segments as a summation. I'm basically going to copy what's above now. And then, now that I got it like this, I got the limit as n approaches infinity, and I got this whole thing, the sigma with the delta x at the end, I can use the definition of a definite integral to rewrite this as an integral. Except, does anybody have an idea what am I going to put in place of delta y over delta x? Yeah. That's dy dx. That's our derivative. So, arc length looks like this. It's the integral from a to b, wherever it starts, wherever it ends, of the square root of 1 plus the derivative squared dx. And that is arc length. Yay! That's our only cloud for today. Because it's Pi Day and it's very sunny. Godzilla! We have the sunshine. See, look at the sun is out. Wow, it's a big bright sun. And it's Pi Day. So we have to put a pie. Maybe some birds. Birds. I know I'm an artist, right? Did you guys do this when you were a kid? Like this is how you did birds? Yeah. We'll put a flower. That's about all. I never moved up from doing it. There we go. All right. Now we got 3 examples. Sophia. Say that again.
Do you replace delta y over delta x with the dy dx?
That's exactly it. Yep. Derivative, slope, rate of change. Yeah. All right, here's our first example. Oh. Sorry. Did you guys all see it? You wrote it down, right? I'll move it up 1 sec. Oh, that's too big. Oh well. I don't like my flower there. I'm going to get rid of the flower. No flowers for us. Flowers for Algernon. It is sad. All right. Here is the example. Anybody ever see the movie Awakenings? Not sure if that's based on a book also. It's based on a true story, though. It's very good. Make sure you have a box of Kleenex, Sandy. It's Robin Williams, though, but he's in a serious role. But it's the same kind of idea. These people are suffering from some sort of disease that renders them kind of, they're catatonic, like they don't respond to anything. They just sit there. Sometimes they walk. They don't respond to talking. They don't talk. It's like they're not even there. But this one doctor comes in and he doesn't give up on them. And he experiments with some different medications and stuff. Anyway, through medications, he's able to awaken them. And they come out and they're there. And anyway, it's just Very powerful. Robert De Niro's in it, too. Playing a very non-Robert De Niro role. So, very good. All right. Now I'm going to put the arc length formula just off to the side here so we have it as a reference. These problems are pretty straightforward, but then again, I mean, it's not the calculus that actually becomes hard. It's the algebra. So you have to be able to find the derivative, square it, add 1, and take the square root. Maybe not. We may end up just leaving the square root and taking we've seen integrals with square roots before. But sometimes, if we can cancel out the square root, that's like an extra bonus. It makes it easier to integrate. So it's just simplifying this thing. And depending on the problem, it can be easy or hard. But that's all algebra. That's not really the calculus part. Because this can be complicated depending on the problem, most people, when they're solving arc length problems, before plugging into the integral, will do that in steps. They'll take the derivative and then square it and then add 1 and see if they can simplify down at all before actually plugging into the problem. So that's the way we're going to do this problem. So the first thing I want you guys to do is try taking the derivative of that thing. I'm going to freeze the screen. And if you're watching the video at home, pause your video. Yay. What? I am, because I messed up the recording first period. So we're going to try again with you guys. So be careful, you're on candid camera. Yeah. Alrighty. This is what you should have gotten for the derivative. You may not have written it exactly like this. Like you may have put it the x to the negative 2 is over x squared. But any questions on the derivative? Because the next thing we got to do, according to the formula, is square it. So now try squaring that. Godzilla. See what I mean about it gets messy. And what you should have gotten when you squared it was this. It really helps if you have this formula memorized. And just remember, if it's got a minus sign in there like ours did, it's minus 2ab. In fact, here, I'll put plus or minus, plus or minus. So square 1/2 x squared, you get 1/4 x to the 4th. For the middle term, I think of it as multiply a and b and then double it. So if you multiply these two together, the x's will cancel out. You add the exponents, you get x to the power of 0, which is just 1. So 1/2 times negative 1/2 is negative 1/4, but you double it, you get negative 1/2. And then that's where this is. So any questions about squaring? All right, so then the next thing in the formula, it says to add 1. So let's go ahead and I won't freeze the screen for this. We're just going to add 1 onto both sides and see if this simplifies it all. Sometimes it does. Sometimes it doesn't. Will this simplify it all? Do I have any like terms that I can combine? Yeah, I got the negative 1/2 plus 1. So 1/4 x to the 4th plus 1/2. So any questions just how I got here? And also see what I mean? It helps to do this off to the side before putting it in the integral. Just take it kind of step by step. And I want to point out something really important, because one thing I did notice on your last test, I noticed a lot of people are getting sloppy about labeling their work. So for instance, let's say I just had this on my paper. Well, if I just have this on my paper, I'm implying that all of those things are equal to each other. Are all of those things equal to each other? Yeah, hell no. And if you start doing things wrong, like if you make a little mistake, I may not even have any idea what you're doing. You haven't labeled anything. So make sure that you do have, the first line is y, the second line was dy dx, but then I squared both sides. And so every step of the way, even when I added 1. The only 2 lines that are really equivalent to each other are the last 2. Every line is different. All right. So now the big question is there anything I can do with that or not? Sometimes we can, sometimes we can't. If we can, we try to simplify it before plugging in, but we're almost ready to finally go to the formula. So what do you guys think? Is there anything we can do with this before we move on? Can we factor it? We can. And actually, if you look closely, the answer to how to factor it is in our work. Anybody notice anything? Akarsh? Exactly. Look at these 2 lines here. Look at this line, specifically this part that I'm highlighting, compared to this part. What do you notice about those 2 things? Yeah, they're identical except for the sign. The minus became a plus. Remember where this came from. This line came from squaring this quantity above. That means this will factor into exactly the same thing, except the minus becomes a plus. It's hard to spot, but it's there. So 1 plus dy dx squared can be written as 1/2 x squared plus 1/2 x to the negative 2. I don't know why I put parentheses. I don't need those. Oh, I do need those because it's squared. That's why. Now this doesn't always happen, but just, things to be on the lookout for. But any questions about how we did that? So this is what I mean. It's not really the calculus that's going to trip people up. It's usually going to be the other stuff, the algebra. But that's awfully convenient that we're getting something squared, isn't it? Because we're going to plug that into a square root. Oh, yes. So now we're ready to work this out. What are my limits of integration going to be? 1/2 to 2. It's given in the problem. So what I want you guys to do now is try finishing up the problem. Plug that into the radical. Take the derivatives, see what you get. I'm going to freeze the screen. And You at home, try to pause the video and see what you get. Fractions are fun. If you're working with an LCD of 24 or 48, depending on how you did it, you're on the right track. You can factor out a 1/2. So you might be using 24, you might be using 48. But then your final answer, anybody know what the denominator is in the final answer once it's all simplified? Did you get something bigger than 10 in the denominator? Did you get something bigger than 20 in the denominator? After it's fully simplified. You might be able to simplify by dividing by 3 over 3. Because your denominator, once it's all simplified, is between 10 and 20. I'll unfreeze the screen now. We don't have the final answer up here yet, but we're almost there. It's down below. But when you plug it in, the square and the square root cancel out. I also chose to just factor out the 1/2 because it just looks so much better. You don't have to. So any questions getting to this point with the antiderivative? Does anybody need anything above where my hand is? Because I'll scroll up otherwise. Okay. Because there's the rest of the problem. Now this was a particularly, I don't know, I think it's kind of cool, like the way that the symmetry turned out. But it's not always this difficult to simplify the radicand the 1 plus the derivative squared. Yeah, check my arithmetic. I see some head scratching. Did I make a mistake? You know me and my arithmetic. Ah.
I did 3 over 4 instead of 4.
Ah! That's okay. Earlier today, because I did the same problem first period, I said that 2 was 12 over 24 instead of 48 over 24. Oops. All right. Anybody still need this? Because then I got another problem that I'm going to have you do all on your own. I mean, we'll check in. But I'm going to have you guys go ahead on your own, take the derivative, square it, add 1. We'll see if we all get the same thing. Then I'll have you find the antiderivative and, plug it in. But like I said, the formula is pretty straightforward. It's just sometimes the expression isn't so friendly. Anybody do anything fun over the weekend? How many people have seen the Batman? On a scale of really good to really bad, where do you put it? I haven't seen it yet. I don't see anything lower than in the middle. That's good. Are you guys already Batman fans? Yeah. It's 3 hours? Oh man, I'm going to have to pee in the middle of that. Don't drink any water for hours before going. Okay, good to know. Thank you. Wow. Did it feel like 3 hours? Oh, okay. Because remember Endgame when that came out? That was 3 hours. That did not feel like 3 hours. I was surprised about that one. All right. Anybody still need this? Okay, here's your next problem. So go ahead and find the 1 plus the derivative squared first, and we'll check in with that. So again, you at home, pause the video. Try it on your own.
It's not added. Yeah, it's just one big thing.
All right, so you should have at least gotten to here. And hopefully you recognized 1 plus tan squared as being equal to secant squared x. Help me spread the word. If you know people in trig pre-calc or STEM, that when the teacher tells them they should memorize all the identities and the trig values, that they weren't kidding. Because you got enough other stuff to memorize when you get to calculus. You don't want to have to be memorizing this stuff at the same time. Oh, those identities. But boy, isn't that convenient? Because when we put it into the formula, we're going to have the square root of secant squared, which is just secant. So you may or may not have to know how to find the antiderivative of secant. Anybody remember what that is? I know, right? Here's a little hint. Go ahead and finish the problem now. Oh, yeah. Oh. Actually, here, let me... Oh, actually, no, it wasn't there. Okay. Anybody have an answer? Bertel. That's what I got. Hey, cool, look at that. Phew. I did it right. Yes.
Wait, for the second part, would it be 1 plus 0 or minus?
Oh, it would be plus.
Not that it really matters for this, but I just want to know for my
You're right, though, yeah. Thanks. Oh, tangent of 0 is negative 0. Any questions on this one? Oh, identities are fun. Lions and tigers and bears. Oh my. What are you guys going to do today for Pie Day? Besides go to Pizza My Heart and have some pizza pie. That's all I'm going to do too. I have to go home for a Zoom meeting at 5:30. Yay! All right, you guys ready for the last one? Here's the grand finale. That's right. Where are the numbers? We'll do this one together because there's no numbers. It's weird. I gotta sit down for this one. Oh my. Now, we're going to start off the same exact way though. So here's the equation. So what's the derivative? Yeah. And that makes sense. It's a straight line. Derivative, slope. Makes sense that it would be the slope. I think this one we can jump right to saying 1 plus the derivative squared then. It all depends on the problem and how complicated it is. There's not much we can do with this though, and just 1 plus m squared is 1 plus the derivative squared. So I guess that's nice. But any questions there? Can I simplify this expression at all? And by the way, if you're thinking, can't we just write it like this? A puppy just died. Yeah, we can't. There's nothing we can do with this. So, I guess we're ready to go to the formula. So, arc length is... What are my limits of integration going to be? Yeah. So, the square root of 1 plus m squared dx. Is it what? Oh, right. Yeah, I was thinking, how are we going to integrate this? But wait, isn't m a constant? So wouldn't m squared be a constant? And then 1 plus m squared is still a constant? You take the square root of that and it's still a constant? So how do we find the antiderivative of a constant? Well, I know what you mean. Yeah, there you go. It'll just be x times the square root of 1 plus m squared. And if you're like, wait, what just happened? Remember, what's the integral of 4 dx? That's 4x plus c. So whenever you integrate a constant, it's just that constant times x for the antiderivative. So we got this. We're just going to keep going with it. Then we plug in. Now, the square root of 1 plus m squared, as we said, was a constant. I'm going to just factor that out. And then plug in x2 minus x1. I guess that's my answer. I wonder if there's anything we could do with this. Like, we're talking slope. M is the slope, right? The slope between 2 points. And don't we know those 2 points? x1, y1, x2, y2? So what if I rewrote m as y2 minus y1 over x2 minus x1. Now that's still squared and in a square root. Ooh, I just made this worse, didn't I? I'm going to do the opposite of that this time. Now I'd like to, I do notice, hey wait, this like x2 minus x1's being multiplied by a fraction with that in the denominator. I can't actually multiply them yet because this is inside a square root and this one isn't. So how about I square this and put it inside a square root? Because then I can go ahead and multiply the two radicands together. So let's see here, what do we get? We're going to multiply that by the 1. That's easy. That's just x2 minus x1 squared. And then we're going to multiply it by the fraction. Remember that fraction is squared. So the x2 minus x1 squared cancels out with the x2 minus x1 squared. Ah, wait a minute. Yeah, look what we got. Does this look familiar? It's the distance formula, which makes total sense. Because the arc length on a straight line is just the distance between the 2 points. What? This is crazy. And I'm pretty sure I read this to you on the first day of school. But it's one of my favorite quotes. I'm going to read it to you again. Let me just find it real quick. Don't worry, I know where this thing is. I'm surprised they don't have that thing bookmarked for that. Doesn't read it every year. Some students try to learn calculus as if it were simply a collection of new formulas. This is unfortunate. If you reduce calculus to the memorization of differentiation and integration formulas, you will miss a great deal of understanding, self-confidence, and satisfaction. Yes. There's some satisfaction here. Just saying. That is the end. I'm going to end the recording.